Okay, so in the previous video we did Thévenin, and in this video we are going to do Norton. But before we do Norton, let's look at source transformation. Assuming I have a voltage source, 10 volts, with an internal resistance or just a resistor connected to it, 2 ohms, all connecting something else like 5 ohms, then this circuit behaves exactly the same as doing this, replacing this with a current source. So this is current coming from somewhere we don't know, and the internal resistance will be in parallel with the current source. That means there should be another branch, else they'll be in series. Then we can put this guy here, 5 ohms. Okay, so how do I make this exactly the same as that? I just need to find the value of this current, and the value of that current is going to be Ohm's law, V is equal to IR, between these two, just the two of them. Forget about this guy for now. So that's going to be 5 amperes. Okay, and this guy remains 2 ohms. Then, assuming we wanted to find the current through this guy, you could have used current divider, and that's going to be the total current 5 amperes times the other resistance, which is 2 ohms, over the sum, which is 7, and that gives us 10 over 7 amperes. Let's see if that's exactly the same current through this guy, and that is the voltage, which is 10, divided by the total resistance in series, 7 amperes. So that confirms source transformation. Okay, so obviously this guy called Norton knew of source transformation, and previously we said Thevenin's equivalent circuit looked like this. So Norton did source transformation and came up with what he calls the Norton equivalent circuit. So instead we have the current source and the Norton resistance the same as Thevenin's resistance, or Rn. Let's give him some credit. So he calls this Norton's current, and your node of interest AB comes in. Okay, so let's just practice this on the previous example and see if we get the same values. So I recall it was 10 volts here. Then we had as a resistor, we had 100 ohms, another 100 ohms, then we had another 100 ohms. But we're interested in the current through this node. So what does Thévenin theory say? Thévenin theory said we have the equivalent Thévenin as this, then our RTH, and Norton is now saying we apply source transformation, call that I Norton, RTH, then our node comes in here. Okay, so what do? We take out this guy, just assume it doesn't exist. I don't want to redraw to keep the video long. and we first put a voltmeter here, then you measure the voltage. And now we don't have a voltmeter. It would have been easier if you had a voltmeter in our paper. So I would do calculation to get the voltage, and we did that, and that was 5 volts. You can see that voltage divider, and that's 100, this 100, because the voltage here is what we are going to measure with our voltmeter, over the sum, because the two are in series, times the 10 volts they are sharing. So this guy gets 5 volts, this guy gets 5 volts, and that's what our voltmeter will see, 5 volts. And that's our Thevenin voltage, 5 volts. And our RTH, now this is a tricky part. Now in most textbooks, you would find the RTH manually, but we just decided to put our current here and rather find the current. So that current we find through this ammeter automatically becomes Norton's current. But you can also use that current to find Thevenin's resistance using Ohm's law. V is equal to IR. So I'm sure you'll be used to finding Thevenin's resistance, but that can be a bit confusing when you hear things like look into the resistor. It gets a bit weird. So for now, let's just keep it simple. Just calculate the current our ammeter is going to read, and that will help us find Norton or even Thevenin resistance and Norton resistance as well. So the current our ammeter is going to read, we did that, and we saw the ammeter, very important. The ammeter is going to short circuit this guy. So that's the only tricky part. If you understand the operation of an ammeter, the ammeter short circuits this guy. You can watch the previous video if you don't really get what you mean by short circuit that guy. So this guy gets shorted out. Ohms. By the ammeter, which has a resistance of 0. Ideally, that's why I shortened that guy out. 0 ohms. Okay, so you can calculate the current through this as 10 volts over 100, and that's 0.1 amperes, and that becomes our Norton's current, 0.1 amperes. Or we can use that together with the VTH to find our Thevenin resistance. VTH is equal to V is equal to IR. Then we have 5 over 0.1, and that gives us 50 ohms. Okay, 50 ohms. So what we have is our 50 ohms here. Then we can put our 100 ohm resistance here. Do the calculation, and we expected to get the same answer by using the current divider rule. So it's going to be 50 over 100 no 50 over the sum, sorry. So 50 over 150 times the current with the 0.1, and 1 over 3. For a moment I thought I was going to get a different answer, and that's 1 over 30 amperes. Alright, so compare this to what you find in a textbook by just finding RTH, VTH, and whichever method is easier for you, you stick to it. It all works. But I personally prefer this because of how practical it feels. It makes you understand how easier it is to use Thevenin, because Thevenin's theory was meant to make things easier, but our textbooks make it seem more difficult. But once in practical sense, you have your voltmeter, your ammeter, and you can just draw this circuit VTH and calculate your RTH by just doing your measured voltage over your measured current. Then you are good to go. You place your load of interest here, and you can easily find the current through your load by doing this plus this and VTH over that sum. Okay, I hope you enjoyed the video. Bye.